This conference will now be recorded.
Yeah, so good evening, Deepa and Selvi, Guna Selvi. So today we'll be learning what happens to the current in the circuit when we apply an alternating voltage to an inductor. Okay, so this is alternating current chapter. We had already learned few things. We had seen in the last classes like what is AC alternating signal, and then if we apply alternating voltage to a pure resistor, what happens over there, whether Ohm's law is valid or not. Those kind of things we have already learned. So today, and also we have learned Phasor diagram representation of any sinusoidal signal. So today we'll be learning what happens to the current in the circuit of a pure inductor when it is connected to an AC source. So let me come to my presentation. Okay, so you can see this figure. Is the diagram visible to you people? So this is an inductor coil. Okay, so AC voltage applied to an ideal inductor. So this is ideal inductor. I am saying ideal inductor. So in general, any wire or any coil of wire will have some resistance, at least some resistance will be there for any inductor coil. But in this study, what we are going to discuss today, we have taken an ideal inductor. So, or a pure inductor. Pure inductor means it has negligible resistance, or you can think that resistance due to this inductor coil is zero. We have connected this inductor coil to an AC source which has voltage across it. V is equal to Vm sin omega t. That means a sinusoidal voltage. Okay, or the voltage is varying as a sine function with respect to time, and it has frequency omega. Frequency of oscillation, it is kind of oscillation. As you know, AC signal, see, sine omega t means the voltage will be varying as sine curve like this. So sometime it will be zero, sometime maximum, again zero. Over a full cycle, again it will be maximum in the opposite side, because sine omega t has its value in between plus minus 1. Okay, so that's how the voltage here in this circuit will be varying. So the maximum amplitude, it is called Vm over here. So this Vm is the amplitude of this applied voltage. Okay, omega is the frequency of oscillation. Okay, if you know the frequency of oscillation, you can find out what is time period of this oscillation, that is 2 pi by omega. So these are the things we know already. So we have got some idea about what we are applying to this pure inductive circuit. Pure inductive circuit means inductor does not have any resistance associated with it, or if it has also, it is very very small, and it is very much possible to neglect that. Okay, now what we'll do, actually what is our agenda over here, we need to know what is the current in this circuit. What is the current? So these are our agenda. So what is the current in the circuit? Circuit I am abbreviating as CKT. Please remember this. This is CKT means circuit. Okay, this electrical circuit. What is the current and how is that varying with time? Okay, that means we are seeing that the voltage is varying as sine function. So what about the current? Whether that is also sine function or cosine function? If it is cosine, whether it is having positive or negative. So that means now we have learned. So these are two things. And another point, actually, these three things we are going to discuss. Another thing is what is the difference phase difference between voltage and current. So this is between, I'm just abbreviating because I don't want to write full since I am speaking. So you can, so this is difference, phase difference between voltage and current. So these are few agenda. Depending on these points, we'll be discussing this circuit. What is that? What is the current? How is it varying? And what is the phase difference between voltage and current? That means what is the relationship between voltage and current? So these are few agenda we'll be looking forward in this circuit. Okay, let us see. So if we want to know the current in the circuit, either we have to apply Ohm's law or we have to apply Kirchhoff's law. Okay, Kirchhoff's voltage law or Kirchhoff's loop rule we have to apply. Okay, basically KVL you have to apply, voltage law, Kirchhoff's voltage law you have to apply. So why? So among these two, see, Ohm's law is not applicable here because it is not a linear circuit. Okay, inductor is not a linear circuit. That means V is equal to IR. This is not the equation which is valid for inductor. Okay, IL, that is the inductive, like current in the inductor circuit, does not vary linearly with the voltage. Okay, that's why we cannot apply Ohm's law. So what you have to apply? You have to apply Kirchhoff's law because it is valid for linear circuit as well as non-linear circuit. Okay, so what is the Kirchhoff's voltage law? If you just remember, we had discussed our previous lectures. So Kirchhoff's voltage law is saying that in a closed loop, the voltage drop or voltage across each circuit element, if you just take the sum of all of them, then that is actually is equal to 0 over a like closed circuit. The voltage across each element, if you just take and then sum them up, that is 0 for a closed circuit. Okay, or in other words you can write, see, summation over IR. If it is a linear circuit, this is equal to the EMF of the battery. Obviously the EMF of the battery you have to take according to the sign. So in this case it is not a DC circuit, neither a linear circuit, so it is not valid. So we'll be just going with this one. Let us see. In this case, see, we have to see what we have in this circuit. We have a battery source which has voltage this V, suppose this is V, which is varying as Vm sin omega t, and you have inductor. So see, whatever voltage you have across this, the whole voltage will be applied across this coil. Okay, whatever voltage you have across this battery will be applied to this inductor. So it is very simple to write the Kirchhoff's law. This is the Kirchhoff's law we can write, uh, or which implies this one. Okay, so V is equal to L di dt. So L di dt, this is the EMF we have learned in the previous chapter. This is called induced EMF in an coil inductor coil. Okay, this is EMF induced in the inductor coil. And look, this di dt is the change in the current. That means, see, this is an AC signal. AC signal means, as I showed, this is a sinusoidal voltage like this. So when it changes its magnitude and direction, or both, either magnitude or direction, or maybe both. So in that case, this is a finite. So this gives us finite value. So this is how, since the current is changing in the loop or the coil, so the flux induced or flux linked in the inductor coil also will vary with time. And since flux is varying, we know flux time varying flux will induce an EMF. So according to Faraday's law in the previous chapter, we have learned that induced EMF is equal to, if you take the modulus of that, so d phi by dt. Okay, again d phi by dt for an inductor you can write phi is equal to Li. Phi is equal to Li, so L di dt, where phi is equal to L into I. Okay, we know that, we have already learned. If you don't remember, just go and look your book, the electromagnetic induction chapter. Okay, phi, that is the flux linked with the inductor, is written as phi is equal to Li, and or phi directly proportional to the current in the loop. Okay, so this is how we can write. This is an EMF, that's why. So anything you just add or subtract, both the quantities have to be dimensionally same. So like here, the voltage, this is voltage and this is EMF, both are actually dimensionally correct. That's why you can write d L di dt, V minus L di dt. I hope you have understood why we have written this EMF in the inductor L di dt, because this is the voltage across this inductor when a current is changing in the circuit. Okay, so now let us see at any instant of time, time t, the current in the circuit is I. Okay, so that's how we can write this equation. Now we have to find out current. Okay, we have to find out current from this equation. So what you have to do mainly, see di dt, I will be writing from there. Di dt is equal to Vm, that is the amplitude of the voltage divided by L. L is the, see, L is here self inductance, of the inductor coil. Okay, so this part is again there, so sine omega t. So if you want to get the current, you have to integrate, right? So let us integrate I current. In the beginning, suppose it was 0, At time t, the current is I. So this side Vm by L integration with respect to time 0 to time t, suppose sine omega t, and this is dt. So what will happen if you integrate this part? Okay, I'll just erase this portion so that I can write this result over here. See, from here what we get is, see, integration left hand side, this will be I minus 0, okay, and right hand side will be Vm by omega into L, because if you just do the integration of this, you will get 1 over omega and minus cos of omega t, and with limit 0 to t. Okay, so you will get actually here a minus sign over here, and you'll get this is cos of omega t. If you just take limit 0 to t, so it is actually uh, it will give you my, okay, so actually if we don't take a limit, okay, so if you take a limit theta is t is equal to 0 also doesn't matter, it will be minus 1. But see, when you take the average of this, so this plus or minus 1, so it will be actually 0, so this constant will be 0. Okay, so in this case there will be no constant factor. Okay, so if I just take without limit, then there should be, okay, I think I'll just write it again here. If I don't take limit, then you have to come up with a constant, integration constant. I'll just tell you what it is. So here I can write I is equal to Vm by omega into L minus of cos omega t. Okay, this is plus integration constant C. So see this constant, because this is a positive, so this is a positive itself, this itself is a positive quantity. Now if you just take time is equal to t is equal to plus or minus, this function does not change, but this will change. Okay, so that's how, if you take the average of this quantity plus and minus c, so it will be 0. That's why the integration constant can be neglected over here. Okay, since this is not a time varying function, it does not affect our current in the circuit. Okay, because DC current does not affect our inductor. This is, so this is a constant part, it does not vary with time. So no, if there is a part of current which is not time varying, that will not influence anyhow in this inductor coil. So that's why this constant term we can neglect. It is okay. So what is the current we have got now? The current, so from here if we solve it, so solving this we'll get current I is equal to, so Vm by omega into L, and this is with a minus sign over here, and cos of omega and t. Okay, so see here this term, first of all you have got a minus sign. See this minus sign I can write cos of omega t minus of pi by 2. If I write this, then there will be minus cos omega t over here. Okay, so this how sorry, I'm sorry, this is not cos omega t, this will be sine omega t minus pi by 2, sine omega t minus pi by 2, this will give you minus cos omega t. Okay, and now let us take this part. So we have learned in the 11th standard that any equation has to be dimensionally correct from both sides. That means, see, this sine omega t, this is dimensionless quantity. dimensionless quantity. Okay, dimensionless quantity. So in the left hand side, this is actually having a dimension of current. Then right hand side also has to be dimensionally, it has to be current. It should have a dimension of current. So since this sine omega t, this term omega t minus sine omega t minus pi by 2, this term is dimensionally less, dimensionless quantity. So this must be having a dimension of current. So this must be having dimension of current. Okay. So if this has a dimension of current, look what we have here. I'll write this as, so finally I'll write the current as Im sine omega t minus pi by 2. Okay, this I can write. Maybe I'll write neat and clean over here. So what we have got is actually Im is equal to Vm by omega L. This is what we have written. So this is, what is this? This Im is the amplitude or maximum current in the circuit. And this is, see, we know from Ohm's law. Okay, if we just bring an analogy, current is actually V by R. So from that analogy, actually we can write this omega L has dimension of resistance. Dimension of resistance. Okay. This must be having dimension of resistance. Okay. That's how you will get V by R is equal to I. So that's why this omega L, I'll just clean everything and I'll write our outcomes. We have got I is equal to Im sine of omega t minus pi by 2. Okay. And we have written Im is equal to Vm by omega into L, where this omega into L is known as, this is known as actually inductive reactance. Inductive reactance. Okay. And this has a dimension. It has dimension of resistance. That means what? In the pure resistive circuit, we have seen the current is Im is equal to Vm by R. So here omega L is omega into L. This is actually serving that purpose of R, omega into L. So these two are actually equivalent to each other. That means I can say that omega into L, it is having dimension of resistance and its SI unit will be ohm. Okay, ohm. This is a symbol of ohm actually. So as you know, resistance has unit SI unit ohm. So inductive reactance. So this is denoted by X suffix L. X suffix L. It is called inductive reactance, similar to resistance in the pure resistive circuit. Okay, and see, you have to remember this omega, see, XL is equal to omega into L. This is called inductive reactance. So XL is directly proportional to omega, the frequency of the signal. Okay, see, you can see one thing, that current has got a phase omega t minus pi by 2, whereas your voltage has got a phase omega t. That means your current is lagged by 90 degree or pi by 2 phase angle. Okay, minus omega t minus pi by 2. This means your voltage is leading and your current is lagging. Your current is lagging behind the voltage in the circuit, which is applied through from this AC source, and the current is lagged by pi by 2 phase than your voltage. Okay, and see, but this both voltage and the current, they have the same frequency. They have both have same frequency, and see, this inductive reactance is directly proportional to the frequency of that signal or frequency of that current, and it is directly proportional to even the inductive reactance. If you want to increase the inductive reactance, sorry, this is L is self inductance. So if you want to increase your inductive reactance in the circuit, you have to either increase the signal frequency, or you can do one thing, you can take a coil, inductor coil, which has more self inductance. Okay, I'll just summarize here what we have learned. So we have learned, see, if we apply a voltage in our circuit, a pure inductive circuit, this is the voltage varying as sin omega t, then we'll be getting a current in the circuit as Im sin omega t minus pi by 2. Okay, that means your current is lagging behind the voltage, lagging behind the voltage by pi by 2 phase. Okay, and what is Im? Im is written as Vm, amplitude of the voltage, divided by inductive reactance, which is nothing but omega into L. Okay, so this is what we have learned over here. We have learned what is inductive reactance, and inductive reactance has SI unit ohm. Okay, now, so you can see this inductive reactance is there, which is actually equivalent to resistance. Okay, in the pure resistive circuit, the resistance, what it does in the pure resistive circuit, resistance oppose the current or limits the current in the circuit, oppose the flow of the current or limits the flow of the current in the circuit. And we are saying that in a pure inductive circuit also, an equivalent quantity called inductive reactance is there. So inductive reactance is equivalent to resistance. Generally, this inductive reactance oppose the current in the circuit or limits the current in the circuit. Because of this opposition, a resistive circuit, in a pure resistive circuit, there is a finite average power dissipation. So there is a finite, it is a non-zero quantity. So average power dissipation as a joule heat loss, as a joule heat loss. So we see in a pure reactive resistive circuit, there is a joule heat loss. Okay, because it opposes the current. But the question is, since inductor also has a inductive reactance which limits the current in the circuit, then can we expect that the inductor in the coil, inductor coil in the circuit, whether it also consumes power? This is our question now, whether it is consuming power. We'll see that in the next slide. So okay, before we discuss about consumption of power by this inductor or in the inductive coil, dissipation of power, whether there is a dissipation of power in the pure inductive circuit or not, we'll discuss. And before that, we'll discuss the Phasor diagram for the current and voltage in this pure inductive circuit. So what does Phasor diagram do? Phasor diagram is nothing but rotating vectors. Okay, Phasor diagram, in a Phasor diagram, typically in AC alternating current or in alternating signal, in that context, Phasor diagram has actually two vectors, rotating vectors. Okay, one is voltage, another one is current. Rotating vectors, what it does, it rotates. Okay, it rotates anti-clockwise direction with the same frequency as the signal, and this is one rotating vector. I can take another rotating vector. If this is voltage, this is current, then we can find out the angle between these two, voltage and current, which will give you the phase angle between them. So in this case, see, the phase angle between current and voltage is phi in this diagram. Okay, and we can say that voltage is leading because it is ahead of this. If this is the rotation, direction of rotation, you can see this is the direction of rotation of this rotating vector. So voltage is ahead of current, so we can say that current is lagging behind the voltage, like that we can say. And if the angle between the voltage and current is phi, then we can say that the current is lagging behind the voltage by phi phase angle. Okay, so this is how we'll try to represent the current and voltage in the Phasor diagram for this inductive circuit, pure inductive circuit. You look, this figure has been taken from your book itself in the ncert textbook. It is given. You can see, as I said, see, I'll write the voltage. What we know, the voltage is actually Vm sine omega t. That is what we know, sine omega t. But what is the current we have got in the circuit? Im sine of omega t minus pi by 2. That means what? The voltage is ahead of your current. And what is the phase angle between voltage and current? There is a phase angle 90 degree. See, this is actually having phase. See, omega t is omega t is greater than your omega t minus pi by 2. That means your voltage is ahead of your current. And what is the phase difference between them? If you take the difference, so suppose this is phi 1 and this is phi 2, what is the phase difference? Delta phi is equal to phi 2 minus phi 1, that will be pi by 2. So this is the phase difference between the signals, voltage and current. So we'll just try to analyze over here. The same thing will be able to represent in the Phasor diagram. Look, we have two rotating vector. One is V. So Phasor for voltage. So voltage phasor is denoted by capital V, and current phasor is denoted by capital I over here. Look in this figure A, you have two rotating vectors. One is voltage, another one is current. And what is the angle between this current and voltage? It is exactly 90 degree or pi by 2. Okay. And what is the phase difference between them? That has to be pi by 2. So you look here. So this is omega t, and this angle is actually, if I say this angle is actually omega t, minus pi by 2. This whole angle is omega t minus pi by 2. Okay. I'm sorry. This angle, whole angle is the difference between this angle is pi by 2. The whole angle is pi by 2, 90 degree, and the angle this one is actually pi by 2, or sorry, omega t minus pi by 2, or in other words, pi by 2 minus omega t, whatever you can say. So this is the thing. Okay. See, cos of omega t minus pi by 2, or if you write cos of pi by 2 minus omega t, okay, these two are equivalent to each other, nothing will change. Okay. So that's why, so from this figure you can understand that the angle between this voltage phasor and current phasor, so the angle between voltage phasor and current phasor is 90 degree. So these, so the phase difference, what we said, phase difference delta phi is 90 degree. So in this phasor you can see that. Okay, one more thing you have to understand here, that current we had got I is equal to originally minus Im cos of omega t. Okay, that's why we have drawn this one. I is this way. Otherwise, I would have drawn I here and V here. So that also will make 90 degree. But this again you have to see what is omega t. How much omega t you are taking. So this is the omega t. That's how you have to draw this way. Okay, so that you get minus sign as well. That's why this current phasor is in the fourth quadrant, whereas your voltage phasor in the first quadrant. So which one is ahead? Voltage phasor is ahead than your current phasor. So this is what is represented in this phasor diagram, and we have discussed already that any rotating vector can produce a complete sinusoidal signal. Look, this is the voltage phasor. If you take the projection here on the vertical axis, this part will give you instantaneous value, and the magnitude, if you draw here, this is the magnitude, sorry, this is the instantaneous value over here. If you draw here instantaneous value here, if your vector is here, so rotation, so this is how you can produce the whole sine Vm sine omega t, this curve, this signal you can get from this phasor diagram or rotating vector of V. Okay. Now look the current phasor again. Current phasor also can produce a full sinusoidal current. Here, look here. If it goes here, so current will be here. If it goes, current phasor is here, then current will be here. So like this, it can produce the whole current signal. Okay. And see the projection here on the vertical axis. This part is is actually the instantaneous current in the circuit. So I am sine omega t minus pi by 2. So this is the phasor diagram. So what we look in phasor diagram, we look that what is the magnitude of the voltage, whether it is more or less than the current over here. The current is less magnitude. See the length of the rotating vector will tell you the magnitude of the current. See the voltage has Vm magnitude, and whereas current you have Im, which is actually Vm by omega into L. So this quantity is less than your voltage magnitude of the voltage. That's why the voltage phasor has greater length than the current phasor. Then voltage phasor is ahead by 90 degree or pi by 2 than the current phasor, so which is also represented over here. So in phasor diagram we see what is the phase angle between the two rotating vector, or here current and voltage phasor, which one is lagging behind, which one is going ahead. these things we see, and it has to produce a whole signal itself, okay, just by rotating that particular pressure, okay. All right, so with this we just complete the phasor diagram of this inductive, pure inductive circuit, where we have drawn voltage and current. Now look, we had already asked a question. Since inductive circuit has equivalent quantity of resistance, say one quantity, that is omega L, which is inductive reactance, which is equivalent to your resistance in a pure resistive circuit. And we have seen that it actually produce joule heat loss. It produce, I'm sorry, just a minute. It produces a heating or a loss, okay, in the circuit. What loss? This is a power loss as joule heating. Power loss as joule heating. Okay, joule heating. So in inductive circuit also, this is this limits the current as resistance do in case of resistive circuit. In inductive circuit, omega L, which is called inductive reactance, limits the current in the circuit. And we have seen that resistance produces a joule heating or it consume a power. My question is whether the omega, see this inductive circuit, in a pure inductive circuit, whether the inductor also consumes a power from the battery source. So that is my question now. Now we'll see. Let us write the instantaneous power. We have got instantaneous voltage V is equal to Vm sine omega t. We have got instantaneous current I is equal to Im sine of omega t minus pi by 2. This we have already got. Okay. So now if we want to find out instantaneous power, instantaneous power dissipation. So I'll write a small p, so which I can write as V into I. So then I can write Vm Im. See this I'll write in original form minus Im cos of omega t. This is what I had. I'll write in the pure form. There will be minus sign over here. So you'll have sine, oh sorry, here sine omega t into cos of omega t. Okay, you'll have this. So what I have got actually, you look Vm Im by 2. Then I can write this as, so since I'll get here sine omega t cos of omega t multiplied 2 in front. So this will give you minus Vm Im by 2 sine of 2 omega t. Okay. Now if you take the average, of this power to get average power, okay, average power over a full cycle. So this is instantaneous power. That means at any instant you get this kind of power. But if you just take average of this over a full cycle, average means full cycle of this actually. If you take the average, let us see what we get. Average means you have to take time average. Obviously this is Vm Im by 2, and you have to take average means you have to take the average of this sine 2 omega t. So when you take average of this sine omega t or 2 omega t, sine 2 omega t, this will give over a full cycle, this term sine 2 omega t will be 0. Average of the sine 2 omega t will be 0. So finally what we get? Average power in the circuit. So we get that average power in the inductive circuit is 0. Average power in the inductive circuit, because if you take the average of this quantity, this is Vm Im by 2 sine of 2 omega t. This, if you take the average of this to get the total power or average power of the circuit, so this average will be 0 over a full cycle. So ultimately average power is 0. So what does this signify? This signifies that in a pure inductive circuit where there is no resistance in it, there is no resistance, R is 0 over here, will not consume any power over a full cycle. Okay, over a full cycle it will not consume any power from the circuit. That's why this kind of circuits are called wattless. Current in this kind of circuit is called wattless current. What it does, wattless current, that means there there is no average power loss due to the current flowing in this, or there is no heating in the circuit if a pure inductive circuit is connected with a with an AC source. Okay, there will be no loss of power. Wattless current, that current in the circuit will be called as wattless current. So that this thing will be learning again, wattless current and all. So now let us see physically what does this mean. Average power 0 means what is it and how is it happening that average power is 0 in an inductive circuit. When an AC battery or AC signal is applied to a pure inductor, then how the average power in that is becoming 0, or how is inductor not consuming any power. So this figure is also taken from your textbook, ncert textbook. Look here, voltage, current and power, three quantities have been shown here for a complete cycle. Complete cycle means one full cycle where time period is t. Look, this blue curve I'll write over here. Blue curve represents the voltage, instantaneous voltage. But yeah, so voltage at an instant. Then look, the solid black, okay, solid black, it is representing the current I, instantaneous current. This one is instantaneous current, okay, instantaneous current. And the dashed line is actually instantaneous flask. At any instant there will be flux in the coil because the current is AC current and it is changing its direction and its magnitude. So there will be di dt. So di dt. Okay. So from here there will be change in the flask. Okay. Any coil. So you might be thinking, sir, what is the change in flask? Actually, if you have a coil like this, so in each coil there is current, right? If you just take individual coil, it will produce a magnetic field along the axis. So the other coil, like that, everyone will produce a magnetic field in the direction of it or along its axis. Okay, it will create a magnetic field, and these fields are actually see passing through this circular coil. So that's how we say the flask, and the flask depends on the magnetic field, its direction, etc. So you can see here we'll be analyzing part by part. We'll first take 0 to 1, then 1 to take 1 to 2, 2 to 3, 3 to 4. So these are actually 1. See, this is lambda by 4. This is another lambda by 4. This is another lambda by 4. And then another lambda by 4. So this will give you the full wavelength of the circuit. Or if I say in terms of time period, this is, so this part 0 to 1 is having t is equal to 1 by 4, fourth of the time period. Okay, 1/4 of the time period. 1 to 2 again 1/4 of the time period. Okay, and then 2 to 3 again another 1/4 of time period, and last one also 1/4 of time period. So we have divided the whole time period 0 to 1, that is half a, sorry, not even half, a quarter of the time period. Then 1 to 2, this is another quarter of time period, and 2 to 3 another quarter, and then 3 to 4 it is a complete cycle. Okay, complete cycle. So I'll just maybe show you here in a sinusoidal curve. So look, this part is 1/4 time period t by 4. Another quarter is this part. Then here 1/4 and another quarter is this one. So there are 4 sections over here, you can see there. So we'll be analyzing the power, why the power dissipation does not happen here. So look here, in this when 0 to 1, both the current in the 0 to 1, this is the current, and this is blue is the voltage. So both are having positive sign, or both are positive in sign. So if I just say what is the sign, or okay, so the both are, so this is the instantaneous power for the 0 to 1. Okay, power is positive over this cycle. I'll say why it is positive power. So this is, suppose, see, in a inductor coil, and there is a core material over here. In a inductor coil, the current direction depends on, sorry, the direction of the magnetic field created in that coil, or the direction of the flask depends on the current, in which direction is the current flowing. Suppose in this inductor coil A and B, the current is entering through A, and it is increasing in the positive direction. Look here, the current is increasing like this in the positive direction. So when the current is increasing, that means there is a change in the flask, right? So that is also increasing. So flask also increases, flask link in, since current increases, so flask also increases up to here 0 to 1. Okay, flask is the dashed line, and current is the solid black line here. So both flask, since the current is positive and the voltage also positive, look, the power is also positive. This is the power, this is the power, this is the power, you can see this positive. Okay, this is the power for the each and individual quarter. This quarter, look, this quarter power is positive. So power is positive in the first quarter. So current is flowing from A to B. So you can see from the thumb rule, this is the north pole and the other one is south pole here. And the flask, which is in, including or linking to the coil, is also positive, because your current is changing or increasing in the positive direction. Okay, now look in, so because of that the power is positive, as the voltage and current both are positive. Now we will go to the next part, this 1 to 2. So look, in 1 to 2 what happens? See, your voltage has become negative now. So this is V is negative here. Okay, negative. So 1 to 2 in this quarter of the time period, see, your voltage is negative, whereas your current is still positive, but it is decreasing. Since it is decreasing, the flux also decreases, as you see the dashed line. And when the current is becoming zero over here exactly, then the flux also becoming zero over here. Okay, and since current and voltage they are negative, sorry, current is positive, voltage is negative, so their product, instantaneous power, will be V into I with a negative sign. So there will be a negative sign. So look here, since current and voltage they are in opposite direction, one is in the positive direction, another one is in the negative direction, then the power, since I'm just multiplying V and I with their proper sign, so the power also will be negative over here. So look, first quarter the power was positive and the second quarter power is negative. You can look here, this is the power curve, this is power curve, this one. Okay, this is power curve. So up to 2 we have seen what we have seen, that the current in the coil decreases. See, the current decreases, and at this point current becomes zero, and then further it is decreasing in the negative, or in it is going towards, it changes its direction, it is going towards the negative side, and also its magnitude, or we can say the current is decreasing. Whereas your voltage, look here, voltage in this region 2 to 3, voltage is actually increasing and it is becoming zero over here. So again you look, your voltage and current both are negative, so this is your negative current and this is your negative voltage. Okay, so if you just multiply both negative, okay, then the multiplication will be overall positive. So that's why 2 to 3 this quarter the power is again positive. This is positive. And look now, if we just take average of these two quarter, or for a half cycle, if you take the average power, what is the average power? One is positive, another one is negative, so what you get is zero. Okay, now let us see 2 to 3. In this case I have already told you that the current direction is reverse. So look here, now the current is actually taking entry 2 to 3, current is actually entering, just a minute, yes, 0 to 1 current was entering through A, 0 to 2 it was decreasing. Okay, so 0 to 2 it was decreasing, the current direction is same in the positive direction, that means it is going in the A to A, entering into through A only. Okay, but that current is decreasing. Now this is 2 to 3 means this figure, you look, the current direction has changed now. Okay, oh, I hope, actually I have copied this figure wrongly, so it has to be like this, current will be, okay, I'll just take from your, I'll just show from your book itself, and then I'll explain over there, because my figure is little bit wrongly copied. Let us see here. This third figure, the current is actually reversed. Here you look, this current is reversed in the third, 2 to 3. Current is in the negative direction, voltage also negative direction. So power will be positive. This is the power, positive here. This, if you can see this is the power. And see, the current direction is negative in the reverse direction. That means see B, current entering through B, and see the flux changes. Flux direction also changes. It is in the opposite direction. Look here, the flux direction, this dashed line, this is actually giving you the flux, okay, in the coil. So that is also reversing its direction. Okay, since this is positive, and each time see the instantaneous power are they are actually magnitude wise they are equal, but their sign is different, positive and negative. So what does this positive power mean? That means the circuit, inductive circuit, is accepting, or it is actually taking power from the source, and negative power means it is releasing power to the source again. It is just returning the power to the source. So positive means power, positive means power is absorbed by the circuit from the source. Negative power is negative means it is returning to the source. Okay, returning to the source again. Negative power means. So look, this 2 to 3 again it is absorbing power, and in the fourth quadrant you look, see, fourth quarter of this time period your voltage is positive, current is negative. So current and voltage product will give you instantaneous power, that is also negative over here. That means, see, in this quarter whatever power was absorbed in the previous quarter 2 to 3, now in 3 to 4 this quarter the power is actually again returned back to the source. So why does inductive circuit does not consume power? Because in each quarter of the cycle, okay, so suppose in one quarter the power is absorbed, in the another quarter or the next quarter of the cycle the power will be given to the source or returned back to the source. Again, third quarter of the time period the circuit absorbs power, and in the last quarter of the cycle the same power is again returned back to the source. So power is absorbed and returned back, absorbed and returned back. So if you take the average of all this positive negative etc, then you will get overall zero power consumption by the circuit. Okay, so this is how you can understand. So the current which is flowing in this inductive circuit when an AC signal is applied to that inductor, the current which is flowing through the circuit is called worthless current because it does not consume any power from the source. Okay, so this is how we finish this topic, inductive circuit. Okay, purely inductive circuit. So I I'll stop it here. But if you have any question or any query or any suggestions, you can just tell me now. This is open for discussion now. Guna and Deepa, both of you can ask any question if you have among yourself. Guna, do you have any question? Any portion you don't understand? Deepa, do you have any question? Did you not understand anything?
No, sir.
Oh, you have no question, right?
Yes, sir.
That means you have understood whatever I have taught today. Okay. So if you just read this today, then you will again get better understanding. Just don't uh, forget after listening the class. You just go back and read so that you can learn it properly. Obviously, we'll take up few questions and one class will take up for numerical problems at the end of this chapter. That time I'll understand how much you have understood and how much you are practicing yourself. Okay, anyway, I hope you are understanding and you are reading your textbook properly. If you have any questions, you can ask me anytime. So this topic I have taught today even if we discuss something else tomorrow or day after tomorrow, still you can ask any question in this part, inductor part, or maybe in this chapter any part you can ask me, okay, if you have any doubt. Okay, so I'll stop it here. So bye for today. We'll meet again on Thursday 4 to, okay, Thursday we have our class for 11th standard. Okay, anyway, Deepa is only attending nowadays. All right, uh, we'll stop it here. Bye for today. We'll meet again on Sunday.